In this video, we want to describe an atom within the Thomas-Fermi model. And this is the Thomas-Fermi equations we have just derived. And here, the particular case we are treating is this, it's including this external potential. So when we are analyzing the atom, basically the external potential is going to be the potential corresponding to a nucleus charge set which is located at the origin. So therefore, if we have an electron which is located at position vector r, this electron, the potential which is in this electron is feeling corresponding created by this charge located at the origin is actually this one. So that's going to be the external potential that we do have corresponding to the atom we want to characterize within the Thomas-Fermi model. And in this case, the Poisson equation we have for this external potential is this one here. So basically, this is the external charge, which is an atomic charge set which is located at the origin. And besides that, we are going to define another magnitude, which is this one, which is the effective potential. And the effective potential is going to be the external potential plus the V, which is the induced potential. And in this potential, it corresponds to all the potential which is induced by the electronic charge density, which is located around this external charge set. And it's given by this expression here. Of course, it depends on this induced electronic density around this set. And again, the Poisson equation corresponding to this effective potential is given by the Poisson equation corresponding to external potential that, as we have said before, is this one, plus the Poisson equation corresponding to, in this case, the Laplacian corresponding to the induced potential. And that's going to be given by the Thomas-Fermi equation here. So all the terms in this Thomas-Fermi equation are basically known. So we have just presented, which is the external potential, this is the induced potential, this AK here is this term here, which basically is this prefactor arising in the kinetic energy contribution associated to this free electron gas. And the only remaining one is this mu here, which is the Lorentz multiplier, which is also called the chemical potential. And that's going to be a constant. But what is the value of this constant for that particular case that we are analyzing here? So in order to analyze the value of this constant, of this Lagrange multiplier for this case, it's better to consider a particular range of the R value where this constant is easier to get the value of this constant. Of course, this value is a constant. It's not an R-dependent magnitude. But if it's easier to get a particular R value, which in this case is going to be at very large distances from the nuclei, then of course that will be the same value is going to be at any other point R. The only thing that going to this R to infinity is that at these ranges of the R value, the value of the chemical potential of the Lorentz multiplier is easier to get. And why is easier to get at very large R values? Because as the external charge here is located at the region, and the induced electronic charge is mainly concentrated around this external charge, at very large distances, the induced charge density is going to decay to zero. And of course, associated to that, everything decays to zero. It decays to zero, of course, the external potential. It's going to decay to zero as well, the induced potential, because the electronic charge decays to zero. So the Laplacian of that decays also to zero, because it's actually related to the density, to the electronic density. So everything decays to zero, so that's zero, that's zero, that's zero. So in order to this equation to satisfy, we have that the chemical potential has to be therefore equal to 0. So the Lagrange multiplier arising in these Thomas-Fermi equations, when the external potential we have is this one, it's 0. So that makes actually the equation easier. So this is the equation that we need to solve, and instead of solving that equation, we're going to solve the equation corresponding to the effective potential. Okay, so we are going to analyze which is the equation that the effective potential satisfies. So remember that the effective potential is equal the external potential plus the induced potential. So we want to analyze what's going to be the Laplacian associated with the effective potential, which is this one. And basically we have the Laplacian of that is going to be the Laplacian of the external potential, which is this one, as we have said before, plus the Laplacian of the induced potential, which is given by the Thomas-Fermi equation, which is this one. Remember that the chemical potential for this particular case is equal to 0. And in order for that equation to look nicer, we do have here, this is basically the effective potential. So the Laplacian of the induced potential is this term here times this one, which is this contribution here. So this is the equation that the effective potential satisfies. So we do have now a partial differential equation that the effective potential satisfies here. Okay, besides that, you know that whenever we have these partial differential equations, besides that, it's also important to specify which are the boundary conditions. We need two boundary conditions. The first we're going to specify is the value at very close distances from the origin where this external charge is located, and the other boundary condition is going to be it's associated to very large distances from the origin when r is going to infinity. So for very small distances from the origin, the leading term here is going to be this one. So that's going to be the leading term. So the term associated to the external charge here, and the effective potential associated to this one is actually the one corresponding to the external potential. So very close to the region where the external charge is located, the effective potential is basically going to be the same as external potential here. So this is one boundary condition. And the other boundary condition corresponds to the very large distances from the center, and as we have said before, everything decays. So because the external charge located at the center is localized at the center, we do have that induced electronic density decays to 0, the effective potential has to decay also to 0. So these are the two boundary conditions, and besides that we do also have this equation here. So now we are going to center our analysis on the equation we do have for r different from 0, because actually for r equal to 0 we do actually know what's the solution for the effective potential, which is this one, and for r different from 0 we are going to specify which is the equation that we do have, which also actually is going to be much simpler because this contribution here is only contributes at r equal to 0. So for r different from 0, we do not have this contribution here. Of course, it has an effect, and the effect of this contribution here relies on this one, relies on the boundary condition we do have at r equal to 0. But the equation we do have at r different from 0 is much simpler. It's basically this one. So this is the equation that we are going to consider now. We are going to characterize better, because in our case, even though we do have this partial differential equation here, we do have just one effective variable, because we do have the system is spherical symmetric here. If we just have the external charge which is located at the center, then the system is spherical symmetric. So basically it means that the effective potential it's going to depend just on the R variable. It has no dependence on theta or phi. So therefore, it makes this symmetry, this highly symmetric system, makes the equation we do have here much simpler to solve. And that's what we are going to do next. We are going to specify this equation we do have to solve, considering the spherical symmetry we do have. So the equation that we have for r different from 0 is basically this one, where this is basically the Laplacian we have, where in this case we have just the contribution associated to dependence on the r variable, because there is no dependence on theta or phi, and this term has to be equal to this one. So this is the equation that the effective potential satisfies. So the next step, we're going to make that equations a bit more look nicer. For that, we are going to consider the following. So we are going to write the effective potential in this one, in this way. So first we have this term here, which is the solution we do have for x equal to 0, for r equal to 0, very close to the center, times the t function, where the t function is going to be dependent on alpha, which is going to be a constant that we want to determine. Actually, alpha could be anyone, because all the uncertainty or the solution or what we do not know, the effective potential is going to be included in this t function that has to be determined. So this t function will depend on the alpha, which is a constant that we are going to specify later in order to the equation to look nicer, times x. So in order to, if we consider that answer, if we write the effective potential in this way, and we want to specify which the equation that this t function satisfies, what do have to do is to include or insert the effective potential or effect writing in this way here. So when we apply this second derivative of this term here, we do have the equation that the t function satisfies here. In order to look nicer, this term, we can pass this term to the other side. So that's the equation we do have. That's the equation that the t function satisfies. In order to look nicer, as we have said before, that's valid for any alpha here. And if we want this equation to look nicer, what we are going to do next, we are going to take on a specific alpha value. It's the alpha value, the one alpha value that makes all these terms here equal to 1. So if we take that alpha here, that's the alpha value that makes this term here. Basically, this is done for aesthetic reasons, in order to make the equation to look much simpler. So considering that specific alpha value, the equation that this t function satisfies is this one. So now we do have the equation. Besides that the t function satisfies. Besides that, we do have the boundary conditions. Of course, they are associated with effective potential, but they are, of course, we can deduce easily from here from the boundary conditions that correspond to the effective potential, which are the boundary conditions that correspond to the t functions. And it's easy to see that the boundary conditions for the t functions are the following. So the t at 0 is equal to 1. So that basically means that this is 1. That means that the effective potential is given just by this prefactor here. And when x is going to infinity, when r is going to infinity, the t function has to decay to 0 in order to the effective potential decay to 0 as well. So these are the two boundary conditions corresponding to the t function, and this is the differential equation that the t function has to satisfy. So this is the solution, that's the equation that we need to solve in order to determine everything about our atom within the Thomas-Fermi approximation. We can determine from here the effective potential. We can determine from the effective potential, which is the induced potential, the induced electronic charge located around this external charge. So everything we can determine within for the atom, which is described within the Thomas-Fermi approximation, which, as I've said before, it's somehow it's a kind of first kind of density functional theory. That equation here is not easy to solve, even though there are some analytical analysis. The best or easiest way to solve it is it's a numerical one.